Okay, so it's time to start the next session. So the next speaker is Suvodip Mukherjee. The title is Detecting Gravitational Waves Using a Cosmic Microwave Background. So we have 40 minutes for the talk, and we will have 5 minutes for question and comment. Okay, please start.
Thanks you. And I'd like to thank the organizers at first for inviting to give this talk. I asked to split it into two because I'll be talking on two different topics, one on extremely low frequency from CMB, other on little bit higher and higher from nanohertz to hectahertz tomorrow. And really sorry for not being able to be here. I'm just here until tomorrow after evening. Couldn't stay longer because of some overlapping meetings happening in the country. So really sorry for that. But I have a job to do now, right? I have to tell you about cosmic microwave background polarization and how we can use that to detect gravitational wave background. It's a big topic. My aim will be to make sure that most of you are able to understand the basic interaction mechanism. The takeaway will be what leads to the imprint of gravitational wave on cosmic microwave background. And so that when you go back and read any book, these slides / talk will be useful for you as a tool to understand the technical details better. Okay? So that's the kind of approach which I'm going to take. On this spectrum of gravitational waves, you have possibly heard a couple of different talks already. Today morning, I heard from Gopu on these two areas. He has introduced, and I think on the first of his lecture, he has possibly talked about this one. I'm going to talk about a bit today on what is the detection mechanism for extremely low frequency gravitational wave backgrounds, attohertz or so. So you can, the scope you can see from 10⁻⁻18 to of the order few thousands and even more ever maybe. So it's really a long band we can observe using gravitational waves. And tomorrow I'll be talking about these two in a more technical talk. It's not going to be a pedagogical talk about some of the measurements which can improve our discovery of gravitational wave signals in these two bands. Long story short, which I cannot do without showing these two polarization, these are going to be the key ingredients for me to convince you that we can detect gravitational wave from cosmic microwave background. So these are the two polarization states, right? I mean, if anybody would like to claim that measurement X has discovered gravitational waves, you would like to ask that person, have you measured the two polarization states, or is it a spin 2? I mean, bottom line is that I would like to measure that quantity. So I should be able to convince you that these two has very neat signature on the cosmic microwave background. And this is the typical polarization variations. And you must have seen this plot again and again in this particular meeting, if not before. So when I talk about imprints of gravitational wave, the main key concept is a differential measurement. It's not a measurement of at a point of off time. It's a differential measurement. We go by making a measurement differential in space. You have possibly heard already on the mechanism we do in LIGO-Virgo-Cagra, we do in LISA, we do in PTA. Ultimately, it's a measurement differential in space or differential in time. It's not an absolute measurement. So what can I really use? The cosmic probes at the largest scales. I am going to talk about the smallest frequency, so very large wavelengths. So I have to use some cosmological probes, which is really big, like big scale. You can possibly see this is few kilometers, few millions. This is really the galactic scale, kiloparsec scale, and now you're talking about the largest scales. And on these largest scales, there are two things we have observed in the universe so far, precisely. One is cosmic microwave background. These are the maps in temperature by 3 space-based detectors, and also efforts from ground-based. But long story short, this is the quantity we have measured in large scales. So I can possibly use this. Second is the galaxy surface. Both of them are excellent probe for gravitational waves. Often you hear about the left-hand side part, and as my title says, I will also talk about only the left-hand side part. And the right-hand side part I will talk about after the photo. So ask me how. I'll tell you interesting ways that I was discussing with him today as well. There are other ways as well for detecting gravitational wave backgrounds using large-scale structure. Why am I not talking about it now? Feasible in principle. Feasible currently with the regime, it is possible from current detectors. So this is more likely to happen in immediate time. That's the only reason. In this talk, I am going to focus on these 4 areas. What is the interaction between CMB and gravitational waves? What are the observable of this interaction? Any measurable physics or application-based physics, the first quantity is how it interacts. Second is how I measure that interaction. Third, I'm going to talk about what is the expected strength of that observable. I want to measure something. What is the strength of that observable? And finally, I'll touch upon what is the prospect of detection. I would be very happy to cover all these 3 properly. Detection, prospect of detection, we can also skip if there is not enough time. I'm not sure how much time it will take. Having said so, please ask me questions in between because it's important for you to understand each of these pieces. So the first part, CMB as a probe for the gravitational wave. What is the interaction between CMB and gravitational wave background? How many of you have done some sort of courses that studied CMB? Or how many of you have not studied CMB? Feel free to raise your hand. Good, thank you. So CMB is one of the oldest lights of the universe we see. It's pretty much isotropic. At the first order, it's around 2.7255 Kelvin, which perfectly fits the black body. Remember, this I'll come back later. I'll ask questions on this. Next, I see a dipole, which is of the order of millikelvin. This I removed, I see something of the level of tens of microkelvin. And this whole story agrees very well with a single concept. At the imprint we are seeing is from the epoch of the universe when the very first atoms have formed. Okay? The significance of this measurement is so high that when you make predictions by only 6 parameters, it fits more than 2000 independently observed quantities. It's really a great measurement. So what really happens? Sometime during the universe, so around ratio 1090, ask me a little bit more questions on CMB physics later, but not very required for the next part of my talks. First atoms forms in the universe, and this photon starts propagating, and I see a nice map of that in the temperature field. The question now comes is how would I like to detect polarization in cosmic microwave background? So if I make a first statement that CMB is a perfect black body, how many of you think that there can be polarization imprints? So is this possibly all of you think it now because I am saying I'm going to talk about it, but if I wouldn't say it that way and I would have asked you a question in, let's say in an exam, that if something is a perfect black body, can I have a net observed polarization? The answer is no, this is going through multiple scatterings. So ultimately I'll observe an average quantity which has no net polarization, right? Yes, 100% correct. So a simple way to talk about it, if I give you an isotropic radiation bath, and this is my drawing of an electron, I shine light from left, right, top, bottom, same way, isotropic radiation, right? So this folk has comes here, it oscillates, I see one of those, other one comes, I see one of those, both have exactly same intensity. There is no net polarization. All of you are with me on this? Great. Yeah, so please respond to me, it will help me in moving forward and making sure that these things are getting followed. What's the next part? So can I really have fluctuation? So not on isotropy, but I told you a couple of slides back, starts forming atoms. It may not be happening instantaneously, right? Things take some time to happen. Atoms are forming. And as a result, as I proceed towards forming the very last atom in the universe, it's a finite width. I call it the width during the era of recombination. If so, now I start putting some fluctuation, right? Because entire distribution is happening from scattering between electrons and photons and so on. But now many of the electrons have got into with their protons and formed atoms. So I may have a radiation bar which is in dipolar fluctuation. Means imagine the half of this room on the top is a lot of more photons than the part in the below. So it's like my poor drawing of red is little bit more temperature, green is little lighter temperature. I put an electron in between. Now what's going to happen? Okay, well, this comes here, scatters. This is a little low temperature, comes, scatters. Both of them combine in the field level. Or to really get something, but no net polarization. Both the sticks have the same color. Make sense? You do from this side to this side. This is already a mixed state, so you get some mixed state over here. But the other one, you combine both of them, you do not get any net polarization. So you don't have any hope. So far, whatever I told you, I cannot generate polarization in cosmic microwave background because it's a too nice black body distribution which don't exhibit any net direction of the incoming photon field. As soon as I start going to the next level, quadrupolar fluctuation, now quadrupolar means if I change by 90 degree, I start seeing a difference. All right? So now if I shine photon from top and below in little bit hotter, then on the side at the 90 degree away, this one particularly comes here, oscillates like this, I see this piece. This one comes from this side, this electrons oscillates, and I come like this. Basic electromagnetism, right? All of you can visualize. If I don't shake the electrons, still you can visualize that this is what's going to happen. Don't feel shy to tell no. All of you are with me on this? Excellent. So that means out of these three options, I have possibly convinced you that I would need a quadrupolar fluctuation at least to generate a net polarization in the cosmic microwave background. All right? Now comes the million-dollar question. That is why I am here today to speak about how I generate this. What is the physics? What is the interaction behind it? So first question is fluctuations I have. My example which I gave you, electron I put in the radiation bath is like a fluctuations. So let me try to understand these fluctuations or the simple density field. I have more radiation, less radiation, more radiation, less radiation. It's like a plane wave on the sky. So now if these are my all electrons at different positions, if I just go back to this, you think about this as a unit system. Keep this in your mind as an unit system. Okay? Remaining everything, if this is clear, my entire talk will be very clear. So this is a unit system for you. The leftmost or rightmost, whatever it is. Yeah. Depending on how you are seeing. For you, it's right side. So now I am going to shine quadrupolar fluctuations on these electrons. Okay? So what's going to happen? I have a cold spot, I have a hot spot. All right? This photon comes, it oscillates. So as I have drawn before, it is high fluctuation, less fluctuation. Why it is low here? Because it's a plane wave, right? It's zero, peaks, comes down, again peaks, other side, and so on. Okay? So now I see something less, more, goes down. Now it flips the sign because now this one is this side, this one is this side. So I get this particular orientation of the polarization and I move forward like this. Correct? What is the key signature you are observing here? The key signature is when there is a density perturbations, photons are trying to come from the high density region to the low density region. They're pushing. As a result of which, because of this velocity field, you get a net quadrupolar fluctuation like this, as I have drawn. It's a scalar, don't have any direction. By definition, it's a scalar. So the only possible solution is m equal to 0 for L equal to 2. This goes back to spherical harmonics. And this is what I'm going to get. If this is the direction of propagation, a polarization stick can either be parallel to the direction of propagation or perpendicular to the direction of propagation. All right? Two states. Either it's going to be parallel or it's going to be perpendicular to the direction of propagation. What about gravitational waves? Now here comes the actual introduction part of the physics. This diagram all of you have seen. So if anybody in this room would like to go and discover gravitational wave in whatever band, our job is to make sure we get this piece neat way. We have to convince someone in the room who is going to review that result that we see a field which changes with time in as a spin-2 way. It's a quadrupolar structure. So now I have to convince you how this basic physics get translated to gravitational wave signal. If you are here, get this piece, next piece will be very easier. So let's say you have so far heard about one object, a ring, looks circle, elongated in one way, and so on. So think about an electron sitting at this black dot. Okay? So when it is this particular polarization state, it is coming near the electron. The other one is appearing a little further away. Is that right? Simple. So for an electron, this looks a little hotter, this looks a little colder. Make sense? So on the sky, in this simple diagram, I can now vision in terms of gravitational wave propagating for plus polarization, hot, hot, cold, cold at a 90-degree angle. In fact, this is what you have learned about gravitational wave propagation in any textbook or in any lectures in this meeting. I then go back, no net polarization. I go back to a next state where it is now H plus. So let's say along the y-axis it is elongated. This has gone further away. So now this piece is hotter. Now this piece is colder. My corresponding stick of polarization is going to be this, right? It comes here, it oscillates. I see this one. This comes here, I oscillates. I see this one. Other one I do not see because of projection. Also scattering. So that means if I give you this plus polarization state, I naturally produce a quadrupolar fluctuation around an electron if gravitational wave propagates. I'll stop here for a few minutes and ask, is this piece clear to everyone? If this is not clear, then I'm doomed for the remaining part. Do people, yeah, please.
So what if the gravitational waves are chiral polarized?
Good, very good. So the question is, what if gravitational waves are chirally polarized? So far I have not even talked about anything on circular polarization. I'm only talking about linear polarization. One can get circular polarization and handedness because of that. But again, it's a topic of discussion maybe after the talk, because it's more a little bit more on research level than simple stuff. So at the linear polarization level, how many of you are convinced that this is going to be true, physics-wise? Not because I'm saying. I'm seeing none. I assume you know everything. Then I'll go proceed and ask questions later. Okay, so now the cross one. Cross one is nothing but you rotate your head by 45 degrees, right? So whatever happens here, story is same. I'm not going to repeat it, but all it means that these sticks are going to be rotated by 45 degrees, right? I'm going to have a cross polarization state. Isn't it making sense? So now these two are hot, I see this, these two are cross, I see this, and so on. So plus and cross polarization induces linear polarization in CMB. I repeat again, plus and cross polarization of gravitational waves induces linear polarization in cosmic microwave background, which have different orientation as it propagates. Sentence is clear? The previous part, if you remember what I told you, this piece is going to be the case, or it is going to be the other way, where this is red and this is green, right? You see? Red, green, and red, green. It's a 90-degree flip. This is not a 90-degree flip. This is just goes by 45 degrees. That's the main key signature from this slide you should remember. This is the basic physics part, and possibly this is what I should look on the sky if somebody gives me a job to measure this accurately. Moving on, I will now try to convince you saying that how the plus polarization state will show up on the sky when a mode is propagating. Okay, like I did for density perturbations. So nothing elongated along this direction and so on. So when this is like this, as you possibly remember, it is like over here, I start seeing a polarization state like this. So again, please remember to use that initial diagram as your basics. So now this is cold, cold, hot, hot. I get this one. Similarly, I get hot along this direction. So if I give you a detector and I ask you, please tell me the polarization measurement, what do? You rotate it, right? I see more, this is more, good. So my net polarization is this direction. This is what you're going to do, right? Like we in electrodynamics, those who have done Jackson or Griffith or something, any of your favorite textbooks, you will make the intensity measurement in say IXX, and intensity measurement in IYY, and I ask how much they differ. If they don't differ, I call there is no net polarization. If they differs, I call that particular direction as a direction of polarization, and the amount of difference is the degree of polarization. Make sense? Simple, as simple as that. We are going to do the same stuff here too. It's the direction of propagation, so you now see a plus polarization states. Is it conceptually different from the density perturbation case I have shown you? And how many of you remember? It's not much different, right? See, plus, plus, cross, cross. It exactly looks similar. So density perturbations and tensor perturbations plus states look similar. So what's new I'm talking about? When it comes to cross polarization, now you see this is going to be cold, this is going to be hot. So you start seeing this stick, this particular sticks. Is that correct? So I am now going to see along the direction of propagation, this is the particular orientation. It is no more 90 degree or at a 0 degree angle with the direction of propagation. It is at an angle about 45 degree with the direction of propagation. Make sense? If I ask you a question now, so if I see this from this side, from left to right, and I see from right to left, is there any net change? No. How many of you say no? Okay, I see a few hands. Raise your hand loud and clear. Okay. How many of you see a change on this side? So I start from here, I go to the next one which is here. So if next one I see here, and I see the next one over here. So if I now think about putting a mirror at this point, this one and these ones, and in comparison to these ones are going to change their sign, right? You see, this is changing the sign from this side to this side. It's like an opposite in the mirror image. Correct? So along the propagation and the wave change shows the directionality in the polarization sticks. So that's a very key signature of gravitational wave background for the H cross. This one looks very similar also for the density field, but this one does not, right? It starts changing sign. So now, is it clear? Is this piece clear to everyone? Yeah. Good. You rotate it. That's right. So you can go back from cross to plus. You can do a coordinate transformation and change both of them, but always one of them will show you this. You can choose a coordinate where your plus is cross and vice versa, but in that coordinate system, cross will always show this kind of flip. If I label this oppositely, this physics will not change. It only change, this will go by 45 degree off, this will go by 45 degree off. It only means this goes here. So my argument remains the same. Argument remains the same if I use the very fact that if I put a mirror here, this and this changes the sign. Otherwise, I can rotate my head the way I want and I can get any coordinates. Are you able to follow what I'm saying? Not convinced? Okay, let me go to the next slide, possibly that will convince you. So if I start using the argument of this directionality and go back to this slide, so any distribution of polarization Stokes parameter Q and U, I would now write in terms of plus with something, we call it E mode, that does not change sign under parity. Means if I put a mirror, this always goes to this and so on. Same for this. It does not change parity. It does not change the polarization stick direction. Whereas the other one, if I put a mirror here, this goes here and vice versa. Okay? So the right coordinate to use is a coordinate where they show a different handedness. Because here, this looks very similar to density fluctuations. This looks very different. So my job to detect gravitational waves will be to distinguish between these two states, right? And as you said, I can change the direction, and anybody in the room has at least those many directions, and in principle, you have infinitely such choices. But I can now take a physics ground from this very basic example that this piece always changes sign under mirror reflection. These pieces don't. Is it getting very difficult to understand that any vector field I can now write in terms of two fields? One is with handedness, other is with not. How many of you are with me on this? I can write a polarization state with two different distributions for E mode and B mode. Okay? So this piece shows up for this as well as for this. Means for density fluctuations as well as for gravitational wave, it can show up. But other one don't. That's my key signature, that anything which starts having a handedness is a signature of gravitational wave. Where is the handedness coming from? Is from the very fact that your cross polarization states are not producible by scalar perturbations. That's the key. Okay? So if I write to now put it, yeah. Yeah, that's the usual Helmholtz theorem, sure. That's, yeah, so that's the Helmholtz theorem we're talking about. So, talking about the projection of gravitational waves on the sky, now I purely can say I have a pure E mode. I have a pure E mode in H plus, but I have a pure B mode in H cos, for the example I have given you. So do you follow what I'm doing? I told you at first that Thomson scattering can intrinsically produce a polarized state if there is a quadrupole anisotropy. Then I tried to convince you that such quadrupolar fluctuations will be naturally produced when a gravitational wave propagates from the very, very fact that this piece of the sky will look colder, this piece will look hotter, so I get a net polarization direction. And if I do the same game everywhere, I will get a net polarization direction, which is now having an angle 45 degree with respect to the direction of propagation. That's the key. Density fluctuations can produce and will always produce polarization sticks either parallel and perpendicular to the direction of propagation, other one won't, with a different direction. That's the signature you would like to see on the sky. Yeah.
Hello. Yeah. So I had a small confusion.
Sure.
So these waves are traveling with time. So you would probably like to take some time average with this, like temperature or radiation, whatever. So over the time, shouldn't they like cancel out? Like one part is hotter and the part is not.
Excellent. So so his question is, on the sky, I have to do some spatial averaging, given the value of gravitational wave propagation is speed of light, I can equally say I do a spatial averaging. Having said so, that means I have many waves propagating. Correct. So that means on the surface where the first atoms form, we call it surface of last scattering. On the surface of last scattering, I have many propagation waves. So I should sum it over all of them. That means I should now calculate this entire quantity for a unit direction of propagation to make it for all possible direction of propagation. Make sense? And that is going to be my observable quantity. This is not observable quantity. I'll come there soon. But you are absolutely right. You have to do a average over all possible directions of propagations of gravitational waves. Any more questions for me? So is it clear to everyone that how CMB photons can, in my language, see gravitational waves? So I started by saying we have to measure differences, right? LIGO-Virgo-Kagra measures differences in spatial position. Pulsar timing array measures differences in time. So what do we measure differences here? Differences in the temperature between two directions. Okay? And then we break it down on the physics ground, saying what is even parity and what is odd parity. And that's the game we play to detect, at least to talk about signature of gravitational wave uniquely on the sky. All right? Now I have to come back and convince you this basic physics interaction can be translated to something that is an observable quantity. How much time do I have? Okay, I can see. Thank you. All right, so this piece may go a bit faster because some of them, these maths is maybe already well known to you through your quantum mechanics course, electrodynamics course, and so on. So what I would like, we basically see at any positions on the sky is a temperature fluctuation. It's a quadrupolar fluctuation. It's a dipolar fluctuation. I always use this word, but what is possibly nice thing to do, because we have a spherically symmetric sky or seeing something on a sphere, as I've been taught in basic physics courses multiple times, make sure to choose the correct coordinates to make your life less complicated, right? So the best coordinate system here would be the spherical coordinate system. That means at any part of the sky, I would like to write them in spherical coordinate system. So whatever that all polarization sticks goes to E mode and B mode is mathematically equivalent that I write the Stokes parameters Q and U on the sky in terms of these spherical harmonic coefficients, spin 2 coefficients, and I just define a linear transformations of them to connect it with E and B field. Okay, that's the maths, and I told you the physics a couple of slides back. All right, this has naturally a handedness. And what's important, that's a question he was asking. I talked about different directions, and I talked about different propagation directions of modes. What you possibly now should realize that this summation is now going to give me the summation of all possible values of L. So 2, 3, 4, and so on, as far as you go. How far you should go, we'll come to this on the prospect of measurement, or we talk about it during coffee. Key thing you to understand that the Fourier modes or a plane waves get connected to angular modes in spherical wave. All right, that's sufficient for us to proceed for the remaining understanding of the basic physics. Moving on, I would like to now write a quantity that me, you, all of us can measure and can talk to each other, right? Cosmic microwave background is a pretty up to a very high degree Gaussian field with zero mean, because I'm talking about fluctuations. So I cannot really tell you that this part of the sky is going to be hot and I'm going to predict that for the universe. This part is going to be little colder than that. This is not a quantity I can really say. I can say about a bit summary statistics. One of the most important summary statistics for a Gaussian random field on the sky is angular power spectrum. Like any other power spectrum, it is always the power and the coefficients for that particular mode, famously written in terms of CL. depending upon what you are combining, x or x prime, this gets the corresponding notations. Very easy to understand. Coming back to the Andrew questions before, these are the quantities we can see in non-parity violating physics. In case of any chirality or parity violation physics, something else will show up, ask me later. But these are your 4 observable quantities in terms of the power spectrum. Okay? This is easy, right? This is easy. Yes, thank you. All right. So what is the expected strength of the observation? This comes to the question already being asked. But now, so I told you the basic physics interaction. Then I told you how to connect the basic physics interaction with an observable quantity on the sky, which is coordinate independent. But now I have to make a prediction, right? I have to convince an experimentalist to go build a detector which can measure that quantity. What is the measurability of that quantity? What is the value of CLXX for the physics I told you? That's about this. So in thing for you should remember, gravitational wave imprint is there on temperature, on E mode polarization, on B mode polarization. Density fluctuations imprint is there only on temperature and E mode polarization if there is no secondary anisotropies. This is like a footnote, which is very important, ask me later. But at the surface of large scattering, there is no signature. That means, and the problem issue is, this is way larger than this. That's why we can see structures, but we haven't seen gravitational wave yet. So if I have to give you in this short talk, if I have to convince you, I would like to tell you, let's go for the best. So throw these for detecting gravitational waves. Let's only focus on B mode, which is never contaminated by scalar perturbations. Make sense? I assume. So when gravitational waves are now propagating, universe is getting older. There are 3 main epochs which you possibly should remember for this particular talk. You may have seen different versions of these in this particular meeting. One is, so somewhere here gravitational waves is generated by different physical mechanisms. This is an epoch where universe goes from radiation dominated to matter dominated universe. And this is the yellow line is the place where they are equal in density. Okay? And this green line is the place where they form the first atoms. That's my epoch of recombination or epoch of surface of large scattering. But this never happens instantaneously. Okay? If you want to ask me, do I have a proof of that? I have a proof of that. Ask me why and how later. But this width is a finite within cosmic time, and that shows the width of, typically the width of recombination. For us, for now, these 3 are the most important epochs which will have a distinct feature on the gravitational wave B mode power spectrum. So some equations, propagation equation, you have seen this in different forms or the other. What is important to realize, I have 2 or 3 minutes maybe. All right, you have 3 minutes. So if I take this equation and I am talking about those modes which are practically, this is tiny in comparison to this, you practically see all those modes which are nearly constant. Okay? This doesn't grow in time. In the other limit, when these are, I'll soon show you an image on sub and super horizon. These scales as, the amplitude typically scales as 1 over A. What does it mean? That as soon they enter the horizon, so I have different Fourier modes, right? Wavelengths of different sizes. If they are much larger than the horizon size back in the universe, those modes are not evolving much. They're typically constant. But when you come inside, they all start decaying pretty much like radiation because they are propagating the speed of light. So they start damping with 1 over A in the amplitude, and that's what you are seeing here. And very roughly, we can, I mean, this is a proper way of also doing to show that whatever gravitational background I see today, in comparison to when it has entered the horizon, just because of this scaling, this is what is true. Simple, right? Now comes a little cosmology. This you have to take on the face value. I do not have time to explain this. What is important is that in this particular diagram, now if I say co-moving scale, modes, wavelengths, let's talk about, okay? And with time, and this is my horizon which is growing as 1 over AH, any mode which is not crossing this line yet, we call it outside the horizon. See, this is smaller than this, outside the horizon. Here, this is bigger than this. I call it inside the horizon. Simple. And I do the same game everywhere. And what it means is that any gravitational wave signal which is outside the horizon, anything outside will show a nearly constant behavior, and anything when it is inside will show oscillatory behavior. So it comes down and it starts oscillating. That's what I told you in the previous equation. It's like wave. It comes inside, it's squashing, and its amplitude is coming down as 1 over A. It's nothing more than that. So if I now want to write down the power spectrum of this particular quantity, I would like to tell you that whatever was there during the generation and whatever is there, just this physics I told you, as my evolution, we call it the transfer function. I should take whatever is generated before, I should evolve it with universe time. As he said, I should add all Fourier modes to get the power spectrum. Very simple argument, right? So whatever basic physics I told you, that is your transfer function. You combine that with your whatever power spectrum is given to you. This you do not know unless it's put by hand. That's why pay attention to all the inversion, all the initial condition scenarios people are teaching over here in these classes. And using these angular modes and Fourier modes, what we can now start writing the CLBB power spectrum. So, couple of interesting imprints. The piece, any Fourier modes which has not entered up to the surface of large scattering are appearing like a constant. That's what I told you. So it should appear like a constant. Any mode which has entered in the matter-dominated universe, means after this yellow line, you can see here, this goes as 1 over k square. K and L are related. So in very simple word, this scales as 1 over L to the power 4. Do you agree with me? Transfer function times initial condition gives me a power spectrum which should have a shape something like this with some oscillations. But remember one important thing, nothing is instantaneous. Yeah, 1 minute more maybe. I started, yeah. If nothing is going to happen, but the recombination is instantaneous. There's a finite width to it. That means any Fourier mode which is within the width of reionization is going to face multiple scatterings. This is the exact thing which he was asking me. So that means anything which is outside gets scattered once, twice, but everything well inside gets scattered multiple times. So you average it out. Get an additional averaging in H as 1 over k and in power as 1 over k square. And that's the suppression you see. That's the damping you observe on the power spectrum. And this is, so if I say this is CLBB, a very famous, usually observed quantity is L square CLBB to make it more flat. And you see that this is the scaling. So this is L to the power 0, this is L square, this gets the L square, this gets the L to the power minus 2, this gets L to the power minus 4. That's the envelope of the fluctuation you should observe. Depending upon what physics plays the role of the initial condition, if there is more gravitational wave at the initial condition, this will go up down. If there is more gravitational wave initially at small scales, means large K, means large L, this will tilt. This will go like this. Nothing else. Transfer function I already told you how it goes. Even everything is just multiplication in Fourier space. And that's what you observe numerically. You don't do this by hand because we need a precision of 1 part in 10 raised to 4, 1 part in 10 raised to 5. Analytically, doable, great. But given our number of times we need to calculate it, we usually use computers like CAMB class code. This is a plot from Anthony Shiner and Anthony Lewis. This is the B mode power spectrum which we observe. And I don't have time to talk about any secondaries. So this you can clearly see that this is the L square piece, this is the L raised to minus 2 piece, and this is the L raised to minus 4 piece. So now next someone asks you, oh, I see a break around 1000, where is it coming from? You should at least tell this is coming because of the width of the recombination. Okay? These p's are all those modes which are inside the horizon during recombination. And everything else over here are all outside. Okay? I will not overshoot the time. I will end my talk here. Later part was actually about telling you how these two interesting epochs gives you these lines and the prospect of measurement. But we can discuss about it during the coffee or during later. With this, I will end my talk and take questions. Thank you.
Okay, thank you very much for the very interesting talk. So do we have any question or comment?
I was just wondering in slide 46, could you go back to the slide, please? In this plot, what about the initial bump that we have? So post L equals 10, it seems pretty close to the theoretical spectrum that you showed. Yeah, starting from there. So before that, why is there the bump?
Great. So he asked me questions which allows me to show you more slides. That's not my fault. Okay, so why? So I told you an answer in the beginning. I need to have electrons, which is C's are quadrupolar fluctuations, right? Great, I first formed the first atoms and the universe is pretty much neutral, no free electrons. But if you go out and measure today, any observation will tell you universe is ionized. Means somewhere ionized, here it is ionized, so here it is atom, so means in between it has gone through something as reionized. So you have free electrons with a density much lower. The universe was smaller here, so density has gone down. So what happens, because now you have every electron in any time around here sees a local quadrupole in temperature. Any local quadrupole fluctuation will lead to E mode, will lead to B mode. And, okay, that's what you see this bump here. This is coming from the epoch of reionization. You see the same bump pretty much at the same place, a little different. I can talk about this a lot more. This is what I have worked a lot. Don't have time to talk about this, but this shows you up over there. And this comes from lensing, because any kind of scattering, whether it's Thomson scattering or gravitational scattering, lensing is nothing but gravitational scattering, also can give you B mode polarization. Ask me more questions on this later, but that's one.
Okay, so let's move on to the next section, next talk. So let's thank the speaker again. Thank you very much.